Hey everyone, and welcome to This Explainer. I am absolutely thrilled you're joining me today. We're going to unpack a brilliant case study that proves just how powerful effective communication can really be in the professional world. You know, we so often think of major infrastructure projects as being purely about concrete, steel, and heavy machinery. But what happens when the math is spot on, but the message is just completely wrong? Well, today we're going to learn exactly how targeted, strategic communication can turn a potential multi-million-dollar disaster into a massive, resounding project win. I mean, how do you stop a multi-department infrastructure disaster with just a few well-written emails? It sounds kind of impossible, right? Almost too good to be true. But we are diving straight into a high-stakes, real-world engineering case study to answer this exact question. We're going to look at a scenario where highly technical data had to be translated for a completely diverse group of stakeholders. And as you'll see, stripping away the jargon quite literally saved an entire municipality from a huge headache. Part 1. The Underground Stormwater Challenge. Okay, let's dive into this. To set the scene, we're looking at a major, heavy-duty underground stormwater asset renewal project. And just to be clear, this isn't just patching up a small leak. We're talking about large-scale municipal infrastructure. To pull this off, the engineering team utilized CIPP, or cured-in-place pipe. This is this incredible, trenchless method of rehabilitating existing underground pipes. So instead of digging up the entire road and causing traffic nightmares, you insert a resin-saturated liner right into the old pipe. That liner then cures and hardens into a brand new, structurally sound pipe right there in the ground. Pretty cool, right? Now, the technical stakes here were incredibly high. We're talking about a 400-millimeter diameter pipe sitting at an average depth of 1.2 meters. The original specifications demanded a non-fiber polyester resin liner at a thickness of 15 millimeters. And why 15 millimeters? Well, because this pipe had to withstand immense earth loads, hydrostatic groundwater submergence, and heavy vehicle traffic above it. It had to be tough.
So, the project goes out to tender, and the bids start rolling in. On one hand, we have our original engineering specification, non-fiber polyester resin at a 15 millimeters thickness. But then, on the other hand, we get the contractor's bid, fiberglass reinforcement with silicate resin. Now notice the thickness they proposed. It's exactly the same, 15 millimeters. At first glance, you might think, oh great, they matched our thickness perfectly. But this is exactly where the hidden flaw lies. The contractor proposed a completely different, much stronger material, but confusingly quoted the exact same thickness that was originally meant for the weaker material.
Part 2. Spotting the design discrepancy. Catching this seemingly minor detail was absolutely crucial because it was actually a massive hidden trap. When the technical lead quickly ran the numbers through their calculation models, they uncovered a pretty dramatic reveal. It turns out fiberglass reinforcement provides an elastic and flexural modulus that is more than double that of the originally specified non-fiber polyester. Simply put, fiberglass is ridiculously strong. Because of this massive jump in material strength, the actual required thickness wasn't 15 millimeters at all. It was drastically lower, sitting somewhere between 6 to 10 millimeters to meet those exact same structural safety standards. Leaving it at 15 millimeters is basically like ordering heavy tank armor when you really only need a bicycle helmet. Now, you might be asking yourself, okay, so what's the big deal? Isn't a thicker, stronger pipe always better? Absolutely not. If this error wasn't caught, accepting that 15 millimeter bid wouldn't just waste a ton of council money, it could physically ruin the project. A 15 millimeter fiberglass liner is severe structural over-engineering. More alarmingly, forcing a liner that thick into the existing pipe would create massive curing stresses on site. We're talking a high probability of physical installation failure. The pipe could quite literally crack or fail to set properly under its own thermal and physical stress. And yeah, of course, paying for 15 millimeters of fiberglass when you really only need 6 millimeters results in highly inflated and completely unnecessary project costs. Part 3. Tailoring the technical message. Because, let's be real, knowing the technical answer just isn't enough. You actually have to communicate it to people who speak completely different professional languages. And this brilliantly illustrates the solution. If the technical lead just forwarded a dense spreadsheet of elastic modulus calculations over to the procurement team, their eyes would just glaze over and the project would stall out. To avoid overwhelming non-technical staff with raw structural mechanics, the audience had to be carefully segmented. Procurement and the project management office care about business impact, so they get a high-level executive summary. The engineers care about mechanics, so they get the math. And the contractor cares about their bid, so they get a formal request for information. Let's break down exactly what each of these messages looked like in practice. For the procurement and PMO folks, the message was distilled down to pure, simple business logic. Stronger material requires half the thickness. A 15mm liner will cause unnecessary material costs and physical installation issues. I mean, that is communication perfection right there. All the complex equations regarding earth load, drainage, and flexural modulus were completely bypassed. The technical lead focused purely on practical impacts. We don't need this much material, and if we use it anyway, it's going to break our budget and fail on site. The decision makers had exactly what they needed to halt the approval, without needing a civil engineering degree to understand why. But you obviously can't send that simplified summary to the civil and drainage engineers. They need the proof, right? So, to contrast the PMO approach, the technical team received a comprehensive, detailed spreadsheet model. This model provided a direct comparative analysis of the elastic and fracture modulus between the two materials. It mathematically proved, beyond a shadow of a doubt, that structural integrity and safety standards would be fully maintained at that drastically reduced 6mm thickness. The engineers got the deep, raw data they needed to confidently sign off on the design change. And finally, there's the contractor who actually submitted the flawed bid in the first place. Now, it would be really easy to just send an aggressive email accusing them of overcharging or making a stupid mistake, but instead, the technical lead issued a professional, clear request for information, or an RFI. This calmly prompted the contractor to just re-verify their own structural design calculations for a fiberglass liner. So instead of pointing fingers and creating this high-stress, adversarial environment, the contractor was given a collaborative pathway to optimize and fix their own bid. It allowed them to save face while aligning perfectly with the project's actual needs.
Part 4. Collaborative Problem Solving.
So, what were the actual business outcomes of this segmented crisis translation strategy? The wins here are literally phenomenal. Because the communication was tailored so perfectly to each group, the bid was quickly and smoothly reevaluated. The contractor rapidly adjusted their design down to the appropriate 6mm thickness, and by doing so, they preserved the structural integrity and the hydraulic capacity of the stormwater line. They completely eliminated those dangerous physical installation risks and curing stresses out in the field. And ultimately, this secured significant cost savings for the council, all while maintaining the original procurement timeline. Translating complex physics into tailored messages literally saved the project's budget and schedule.
Part 5. Principles of Stakeholder Engagement.
Okay, so how do we take the lessons from this pipeline case study and actually apply them to our own careers? Well, these are the 3 core principles for daily stakeholder engagement that you can apply immediately, no matter what industry you're in. First, active listening and empathy. You really have to recognize that different departments have fundamentally different priorities. Procurement cares about cost and compliance. Operations cares about maintenance and longevity. You must listen to those priorities before you even speak. Second, clear and jargon-free translation. Make it a hard rule for yourself to turn dense, technical concepts into actionable, simple insights so that all decision makers feel confident. And third, proactive transparency. Notice how that error in the bid was handled. Address technical gaps early and treat design errors not as roadblocks to fight over, but as collaborative opportunities to optimize. These 3 steps are the ultimate blueprint for fostering trust and maintaining excellent working relationships across completely diverse teams. Which brings us to our final thought for this explainer. The next time you spot a critical error in your own work environment, will you treat it as a massive roadblock, or will you use it as an opportunity for true collaboration? Complex data is only ever as good as our ability to explain it to the people who need to hear it. Thank you so much for joining me today. I highly encourage you to approach your next complex data challenge with the strategic, empathetic communication we've explored here today. Until next time, keep learning and keep explaining.